This clip will try to clarify some IV notation, partly because Woodridge is using two sort of different approaches. The first of the two approaches, I'll soon label it A, starts out with stating a particular model you're interested in. So here we have a dependent variable y, and we have explanatory variables x1 and x2. Now, x2 we say meets the zero conditional mean assumption, so it's unrelated to the error term u1. However, x1, let's say, is correlated with the error term, so that's certainly a problematic variable. We also call this variable an endogenous variable, whereas x2 is exogenous. So that's the basic setup Woodridge also starts out with, although he starts with a simple regression model, but I added a second explanatory variable. Now the second approach, so that we'll say is approach A, the second approach doesn't really start with a model, but in a way just with a list of two categories of variables, and Woodridge adopts this from chapter 15.2 onwards. And the two different categories of variables we are thinking about here are the endogenous variables, and indeed we may have m of these endogenous variables. Note, in setup A we already had two, y and x1, but now we label all endogenous variables y, so y1, y2, let's say up to ym, that's just an arbitrary m. And we shall have k exogenous variables, and we shall label them z, so z1, z2, all the way to zk. So we'll either have endogenous or exogenous variables. So we will have to make up our mind whether the x's in approach A, whether they are endogenous or exogenous, and put them in one of the two categories. So when you have this sort of setup, you can write down what we call reduced forms. And these reduced forms exist for all m endogenous variables. So we can write the reduced forms down for variables y1, y2, all the way to ym. Now, the reduced forms will explain one endogenous variable at a time as a function of all exogenous variables. So here's z1 to zk. Okay, and we'll add some error term, and we can put some coefficients. I'll put some arbitrary coefficient names to them, gamma 0 plus gamma 1 plus gamma 2, all the way up here to gamma k. Okay, and then exactly the same for y2. I'll leave the coefficients away, but you can complete the gaps in your mind. Just have coefficients to each of these z1s to zk's, and then we have an error term. And we will have m of these reduced forms. And they are basically just existing for this entire system of n endogenous variables and k exogenous variables. So let's think about a particular model now. We hadn't really thought about a model now. So in that model we're going to write down is going to be basically the same as the model we wrote down under approach A. So we'll pick, let's say, the first endogenous variable. That's a function of the second endogenous variable and one of the exogenous variables, z1. And here the endogenous variables on the right hand side is y2, and that's the same role as the x1 in approach 1. And x2, the exogenous explanatory variable, is now z1. So in a way this is just different notation. So let's return to setup A and write down the reduced form in the context of our model in A. In general, the reduced form looks like this. We take our dependent variable, which is also an endogenous variable, of course, and we write it down as a linear function, but I write down here f, any generic function, a function of all exogenous variables. Okay, so the dependent endogenous variable is a function of all exogenous variables. So in the context of this particular model, this now means that y is a function of a constant gamma naught plus gamma 1 x2 plus gamma 2, and now we're talking about instrumental variables, we need an instrument, because we can't include the endogenous variable because that's endogenous and not exogenous. So we use an instrument, the conditions of which is that it's correlated with x1, the endogenous variable, but uncorrelated with u. So that goes in here into the reduced form, and we have an error term. So let's move back over to our framework B. For the particular model now that we wrote down, the reduced form is in fact one of the many reduced forms we've already written down, and basically it's the one which uses our dependent variable y1 in the context of our model as the variable on the left hand side, and then all explanatory variables on the right hand side. So when we're doing two-stage least squares to estimate our regression model using an instrument, we then need to write down what the first stage regression is. And that's the explanatory variable that is endogenous. Okay, that should actually read explanatory endogenous variable, not explanatory dependent variable. So explanatory endogenous variable as a function of all exogenous variables. So x1, which is our explanatory but endogenous variable, as a function of x2 and z. Now, in the context of setup B, the first stage regression for model, let's call that the hash model here, model hash, is that we have on the left hand side our explanatory but dependent variable y2, which is the explanatory but endogenous variable y2, and that is a function of all exogenous variables, and that's all the sets. Okay, so we call that the first stage for model hash. But if you look at it, that actually looks exactly like the reduced form for y2, one of the reduced forms we wrote up for the entire setup. I'll get back to that point. So that's our first stage, where we basically model our explanatory but endogenous variable. From that first stage, if you estimate that by OLS, you can get predicted value for that variable, either for x1 or for y2, whatever form you use. Estimate the first stage by OLS and you get predicted values. Then we go to the second stage. And the second stage is basically our original regression model, so y as a function of beta naught plus beta 1 times, but now instead of x1 we use x1 hat, and then plus beta 2 times x2 plus a slightly new error term u2. It's not exactly the same error term. Then the second stage in the context of model B, of approach B, is again our model, which we wrote down as hash, but we replace the y2, which is endogenous, with y2 hat, coming from the first stage regression. So the nice feature of this second stage is now that if we use OLS to estimate that second stage regression, right, so we apply OLS on the second stage regression, we get an estimator for beta 1 hat. So it's in a way an OLS estimator on the second stage, but we also call that beta hat IV, the instrumental variables estimator of our original model. And of course we like the IV because for large samples it has no bias. So let's go back to approach B and look at that first stage regression for that particular model, where we have y2 on the left hand side. That of course appeared as one of the reduced form models we've written down, and that's sort of how Woodridge calls it in chapter 5.2 as well, and it appears in the lecture slides as well. But really in approach A, that was the first stage regression. So it has a double role. It's the first stage and the reduced form for y2. Let's look at that first stage, what it does. On the left hand side we have our endogenous variable x1. So it's an explanatory, but endogenous variables, it's correlated with the error term. Let's separate. What that first stage does is it divides the variation in x1 into coming from two sources, what we would call the explained bit, it's the part on the left hand side, and once we estimate it we can get x1 hat as the explained bit and the unexplained bit v hat. Now that explained bit turns out to be uncorrelated to the error term. The reason is we used z and x2 as the explanatory variables here, and both of them are uncorrelated to the error term. So the linear combination of them is as well. That means the correlation has to come from that v hat part. And then we use that nice part x1 hat, which is uncorrelated with the error term, as an explanatory variable in our second stage regression instead of x1. And then we can apply standard overlays to this.